Welcome back to part 2 of areas and distance. As we saw from the previous two examples, it becomes really important for us to be able to find the exact or approximate area between a curve and the x-axis to find various values in the real world. Let's do more of these approximations, but now let's use functions. Suppose we wanted to find the area underneath the curve f of x equals x squared between x equals 0 and x equals 1. So in the left graph, we have our function curve y equals x squared, and the highlighted blue area we're calling S to represent this shaded region, and we want to find that exact area. But once again, notice that this has curvature, so if I wanted to find the area of that shape, I don't have a formula yet to be able to do that. It almost looks like a triangle, but it's not quite a triangle since we have curvature. So what we're going to do once again is we're going to estimate the area underneath the curve by drawing rectangles underneath our curve and then finding the areas of each of those individual rectangles and adding them together. Now in the previous example, we drew our rectangles so that its height was given by the middle or midpoint of each of our subintervals. So in this case, what we're doing is we are breaking up our interval into 4 subintervals. So we have from 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and 3/4 to 1. So those are 4 subintervals. Why do we have 2 different pictures here? Well, in the middle picture, what we're doing is we're drawing our rectangle so that its height is given by the right endpoint of the subinterval. So on the subinterval from 3 to 4, we are drawing our rectangle, and then its height is established by using the right endpoint, plugging that into our function, and then we see that that's the height of our rectangle. So that's what's happening there. And then in the other graph that we have, if I'm looking at a subinterval, the height is dictated by the left endpoint. So in this case, our subinterval is from 3/4 to 1. So its height is dictated by whatever the function value is when we plug in 3/4, and then we're drawing our rectangle that way. So these rectangles have names, and the one here is called a right-handed rectangle, and this one is called the left-handed rectangle. And we're going to use these again to estimate the area underneath our curve. So why don't I go ahead and draw the rest of our rectangles. Okay, and if I were to take each of these rectangles here and find their areas and add them together, that's going to give me what I'm going to notate as R4. And again, just like in the previous example, I'm using the capital letter R because I'm using right endpoints for my subintervals, and I've broken up my main interval from 0 to 1, and I've broken it up into 4 subintervals, so that's why we're calling it R sub 4. What do you think the estimated area under the curve in the last picture is going to be called? If you guessed L sub 4, you are correct. So R sub 4 and L sub 4 are going to have 2 different values since they have different sized rectangles. And if you are able to make this observation, L4 in this scenario is going to be an underestimate of our calculation or our estimation for our actual area under the curve S. And the reason it's going to be an underestimate is because look at all this area that's underneath the curve. that we're not accounting for. It's that white space there. And then for our estimation for R sub 4, that is going to be an overestimate in this scenario, since we have this stuff above our curve that we're accounting for that's not actually underneath the curve. So let's keep that in mind as we are calculating R4 and L4. Okay, so it says show your work below for computing R4, which is the approximate area underneath the curve using right endpoints and 4 subintervals, and also L4, which is the approximate area underneath the curve using left endpoints and 4 subintervals. R4 and L4 are called Riemann sums. So let's go ahead and calculate R sub 4. And coming back to our picture that we saw above, we know that the area of each of these rectangles can be calculated by figuring out the width. So in this case, the distance between 0 to 1/4 is 1/4. Same thing, the width from 1/4 to 1/2 is 1/4. These all have a base length or width of 1/4. So let's calculate the area of the first rectangle. It has a base of 1/4, and its height is given by f of 1/4. And then the next rectangle has a base of 1/4, and its height is given by f of 1/2. Then our next rectangle has a base of 1/4, and its height is given by f of 3/4. And then my last rectangle, notice that there should be 4 calculations. So this represents the area of my first rectangle. This is my second rectangle. This is my third rectangle. So I need one more, and that one is given by 1/4 times f of 1. And that represents the area of my last or fourth rectangle. And we have our function. We know that y is equal to x squared, so that's the same thing as saying f of x is equal to x squared. So we can actually calculate these values. And also notice that each of our subintervals have the same length, which is 1/4. So what I'm going to do is I'm going to factor out 1/4 since every term in our sum has a 1/4. So now all I need to do is I need to calculate these values into our function. All right, so I went ahead and I plugged those numbers into our function, and I went ahead and I simplified that as well. So let's do our final simplification. We have 1/4 times. If I add up these fractions together, that's going to end up giving me 30 over 16, and that is equal to 15 over 32. And I'm going to go ahead and put that as a decimal. So our decimal value is 0.46875. So that is how we calculate R4. Maybe you should pause the video here and try and calculate L4 for yourself. All right, so let's look at the image or graphic that we have for L4. The height of the first rectangle is dictated by 0 here, and really the height of that rectangle is 1/4 times f of 0, which is equal to 1/4 times 0 squared, which is 0. So it's kind of odd, but that first rectangle actually has an area of 0 because its height is 0. So then what we do is, so that was our first rectangle. Then our second rectangle's height is going to be f of 1/4, then f of 1/2, then f of 3/4. So notice how that's a little bit different than the right-handed rectangles, because for those we used 1, 3/4, 1/2, and 1/4 to calculate the heights, but now we're not using 1, so all of the heights kind of shifted over to the left x value in each of our subintervals. So let's get to calculating L4. Now, just like previously, all of them all the terms in our summation or sum will have a 1/4, so I'm going to factor that out. And then the heights of our rectangles will be f of 0, f of 1/4, f of 1/2, and then the last height will be f of 3/4. So I went through this kind of quickly since we did it already for R4, but notice that a lot of the heights are going to be the same as well. So 1/16, 1/4, 9/16. So it's kind of like it shifted over 1. And so a lot of those heights are going to be the same since we're looking at the same rectangles. And if we simplify this value, it's going to be 7/32. And as a decimal, that's 0.21875. So there's our final answer for L4. And then the next question says, what can you conclude from these two calculations? So remember earlier we said let S equal the exact area under y equals x squared from x equals 0 to x equals 1. The conclusion that we can make from the calculation that we just did is the exact area is going to be greater than L sub 4, because we said L sub 4 was going to be an underestimate, and it's going to be less than R sub 4, since we said earlier that R sub 4 would be an overestimate. So that's the conclusion that we can make in this scenario.